Hello, we are going to start off with the refraction through a single spherical surface, which would lead us to the case of the lens maker formula. First up, refraction through single spherical surface. Here again, we're going to use a single convex refracting surface, which is separating a medium 1 from a medium 2, where the medium 1 has an absolute refractive index of mu1 and medium 2 has an absolute refractive index of mu2. This is only a single spherical surface that we are considering right now. And here's the principal axis. And then we would consider a point object to be at the point O, from where the light ray would be incident on the curved surface of the interface separating the two media. And if we are to consider a normal at that point of incidence, then the normal obviously would reach the center, because that would form the radius, because till the center, the line or the radius from the center is always perpendicular to the tangent drawn on the surface. So there we have the angle of incidence, and then uh, it gets refracted, and the refraction is supposedly through an angle R over here. Now that touches the principal axis at this point where the image is formed, the point I. We take the center of curvature of the curved surface to be at the point C. The point of incidence, I'm taking it as M, and I'll take point P, which probably behaves like the pole in case of the mirror. And in this case, it's just the point P, which is more or less the pole of the lens of the curved interface. Now I can drop a perpendicular from the point M over to the principal axis, and there we'll have a P dash. Now, for the curvature being less pronounced, the points P and P dash, they would be almost coinciding with one another. So if I take MP, I would be considering MP dash as well. So because the curvature is very low or very less, we are considering very small or paraxial rays, or almost rays closer to the principal axis. So the angles thus involved will be very, very small. Now, to mark the other angles, I'm using another ink for that. We'll consider the angle that the incident ray makes with the principal axis. Let that be an angle alpha. Then we consider the angle subtended by the normal onto the principal axis, and let this be equal to gamma, while the angle subtended by the refracted light ray, that is supposedly beta. So we have three angles over here, alpha, beta, and gamma, with respect to the principal axis. And then we have the angle of incidence and the angle of refraction as well. We will be considering a few triangles over here, and more or less they are right angles, MP dash. Now the points P and P dash almost coincide, which means that the segment MP is almost straight. And therefore, what we are, uh, this assumption that we have drawn right now, from which criteria are we getting this kind of an assumption? Are we able to take this kind of assumption? That's because the angles involved are really small. Alpha, beta, gamma, they're all very small angles, and so are the angles I and R, that is the angle of incidence and the angle of refraction. They are small angles as well. So taking into consideration the small angles, this MP is almost a straight line, and it's perpendicular to the principal axis, as you can see. So P dash and P, they are almost the same thing. Now what we do is we have three triangles over here, uh, uh, the first one being uh, OMP triangle. That's a right angle triangle, and from that, rather I would take the first one, that is OMC, the big triangle. And from that, what I get to know is that I is the exterior angle, which has to be the sum of the two interior opposite angles, that is alpha plus gamma. And then I have the triangle MCI. In the triangle MCI, I have the exterior angle to be gamma, and that is equal to the sum of the two interior opposite angles, that is R and beta, as you can see. From that, what I can get is R is equal to gamma minus beta. I hope you can spot the difference between R and gamma. Not a big deal. Now, as the light gets refracted from the first medium to the second medium, what I get from Snell's law is that I have mu1 times of sine I to be equal to mu2 times of sine R. But remember, I and R, they are small angles. So for small angles, what I have is sine theta can tend to theta, and that can be equal to tan theta, for theta being very small, varying especially between 0 to 4 degrees. Now, this mu1 now gets multiplied to simply I, and mu2 gets simply multiplied to R because of this criteria that we have over here. And that results in mu1 times of, well, we can now substitute the values of I and R that we have obtained, that is alpha plus gamma. And then we have for R, we have gamma minus beta. And then we can further take take the tangent of these angles, because these angles can be equated to their tangent for smaller angles considered. So we have tangent of alpha plus tan gamma to be equal to mu2 times of tan gamma minus tan of beta. Now for tangent, we'll be using those two right angle triangles, MPO or OMP you can say, and MPI. So mu1 in the first triangle, that is OMP dash or OMP, you can take it, they are both the same. So we have tan alpha to be equal to the perpendicular, that is MP, well, we can take MP dash as well, so no problems with that. MP dash over P dash O plus tan gamma, that will be equal to MP dash over P dash C. And then on the other side, for tan gamma, we have the same thing, MP dash over P dash C. And finally, for tan beta, we have MP dash over P dash I. Now, the distances that we are considering from these, from P dash, on both the sides, the object obviously lies at the object distance U, the image lies at the image distance V, and for the center, we have that to be equal to the radius of curvature of the given lens, a single surface. So we substitute these values. What we get over here is that MP dash, being the same for all the terms, can be taken common on both the sides, and they can cancel out each other. And from that cancellation, what we get is we have a mu1, and now we follow the sign conventions that we have been using. That is, to the left we'll be taking as negative, and to the right we'll be taking them as positive. So this one is 1 over minus u, plus this is 1 over P dash C is equal to the radius of curvature. So this is 1 over R mu2 times of 1 over R minus 1 over V, which is obviously positive, but the negative sign remains because of the equation over there. So now we can rearrange, and while rearranging, what we get is mu2 over V can come onto this side and become positive, mu2 over V, and mu1 over U, that remains So mu2 over v minus mu1 over u. That is now equal to, well, mu2 over r stays as such, and mu1 over r goes to the other side and becomes negative. So we can take 1 over r as the common factor, and we have mu2 minus of mu1. So that's 1 over r times of mu2 minus mu1. So this is the general condition for the refraction through a single spherical surface separating a pair of media. In this case, the media having the refractive indices as absolute refractive indices being mu1 and mu2 respectively for the first and second medium. Now we will be extending this to the lens maker's formula, which of course will be established in the next video. So thank you for watching, and that's it from this one. Thank you.